In this video, we're going to continue our discussion on indefinite integrals and learn how to do some more complicated indefinite integrals using the technique of substitution. Sometimes this technique is also called u-substitution. So let's start by just defining this technique. It says that if u is some function g of x, and that is a differentiable function whose range is an interval I, and f is continuous on that whole interval, then the indefinite integral of f of g of x times g prime of x with respect to x is equal to the indefinite integral of f of u with respect to u. So what this is doing is we're actually going to be undoing chain rules using our integrals. And this is one of my favorite sections because we get to take really terrible looking, complicated looking problems and hide it. We're going to hide the complicated stuff inside of a new variable and make it into something much easier to solve. So it feels a little bit like math magic, I guess, but it's not magic and it actually works and it's based in real mathematics. So it's going to be a lot of fun. The best way to learn substitution is just to jump right into it and do a lot of examples. So the rest of this video is going to be just example after example so we get the hang of this. So first example, we're going to find the indefinite integral of 2x times the square root of 1 plus x squared with respect to x. Now, this problem, before we learn anything about substitution, would be very, very difficult to do. It's asking us to find an antiderivative of 2x times the square root of 1 plus x squared. In other words, can you find a function that when you take the derivative of it, your result is all of this stuff inside my integral? That is much more difficult than our last video where we were just undoing things with the power rule or using our trig functions, things that we know the derivatives of very, very well. So how do we do a problem like this? Well, most of the time you're going to find something that's the most complicated thing in the problem and hide it inside of a new variable. So what I'm going to do is I'm going to take everything underneath this square root and set it equal to u. So I'm going to have u equal everything under the square root. Now remember, in my whole description of substitution, we had to have u as a differentiable function. So let's go ahead and find the derivative of this guy. du dx is equal to 2x. And now notice, if I treat this symbol for the derivative of u with respect to x, if I treat it as a ratio of differentials, I can write that du is equal to 2x dx. And now this is when you know this is going to work out beautifully. Take a look at the problem we have right now. Underneath the square root, that's my u. And the only other things I have left to deal with in the problem are 2x and dx. And 2x dx together makes a du. So what I can do is I can take my integral and rewrite it using this new variable. I'm going to have a square root of u, and my 2x dx is now going to be du. And this is a problem that I can do using our techniques from the last video. Let's first rewrite it using a fraction for the exponent, and now I can do my backwards power rule. Add 1 to the exponent, divide by the new exponent. And remember, dividing by a fraction is the same as multiplying by the reciprocal. then don't forget your constant at the end. Are we finished? Almost. My original problem had x's in it. My new problem that I rewrote it as is u's. In order to finish the problem up, I need to have it back in terms of x. How do I do that? I take my u and I plug it back in, and then we'll get the answer. So when I plug my u back in, we're going to get 2/3, 1 plus x squared to the 3/2 power plus c as my answer to that indefinite integral. Don't believe me? Well, why don't we just take the derivative of our answer to see if we get the original problem back again? Remember, that's the way you can check all of your antiderivative problems. Take the derivative of the answer and make sure that it worked out. So let's check it real quick. If I check this derivative, we're going to need a chain rule to do this derivative. My 3/2 is going to come down and multiply in the front. My new exponent is going to be 1 smaller. 3/2 minus 1 is 1/2. And the derivative of my inside function is 2x. Derivative of c is 0. Now look at this. My 3/2 times my 2/3, that cancels out to 1. This guy's in a 1/2 power, so that's a square root of 1 plus x squared times my 2x. And I'm just going to write it in the front so it looks better there. And that is exactly what we had inside of the original integral. So this did work. U-substitution undoes our chain rule. All right, so that was our first example. Wasn't too terrible, and we're going to just do a bunch more examples today. Now on this next example, I'm going to show you a little trick that I've learned that students tend to like while doing substitution. I don't use it myself personally, but a lot of my students have used this trick, and it seems to help them learn how to do substitution. So sometimes I'll do it that way, and other times I'll point it out the way I just did, and we'll see what way works best for you, and you should do it that way. So here's our next example. I have x to the 3rd cosine of x to the 4th plus 2 dx. I want to find the indefinite integral of this complicated function. And we're going to use substitution again. So I need to pick something to be my u. In general, your u should be one of the most complicated things. The thing that's bothering me about this problem is I have a cosine, but the cosine has way more than just a variable inside of it. So that makes it a little more difficult to integrate. So I'm going to rewrite the input for my cosine function as my u. So u equals x to the 4th plus 2. Then we can find our derivative of u with respect to x. That is 4x to the 3rd. This means that if I multiply the differential dx over, we get du equals 4x to the 3rd dx. Now this right here is where I normally just look at my problem and figure out how I need to play with things to get it to work. But a lot of my students really like, at this point, solving for dx. If you solve for dx, you get du divided by 4x to the 3rd. Then a lot of my students really like to take the original problem, plug the u in, so I'm going to have x to the 3rd cosine of u, and then replace the dx with what dx is equal to. Now, when you do it this way, you should get cancellation. That x to the 3rd and that x to the 3rd completely cancel out. If you've done your substitution correctly, you should only have u's left in the problem at this point. You don't want to have u's and x's, so all the x's should cancel out. So when I cancel out those x to the 3rds, what I have is an integral of cosine of u with a du divided by 4. Well, that looks a little silly. I'm going to rearrange this as a 1/4 in the front, cosine of u du. And now I'm ready to find the antiderivative. What function has a derivative equal to cosine? Sine. So I know that my antiderivative of this guy, I'm still going to have 1/4. Antiderivative of cosine is sine. Add your constant. And then all we have to do to finish the problem up is plug our u back in. And so we get 1/4 sine of x to the 4th plus 2 plus c. And again, if you really wanted to, you could check this by taking the derivative. If I take the derivative of my answer, the derivative of sine is cosine, so I would have 1/4 cosine of all of that stuff times the derivative of this inside, so times a 4x cubed. The 4's cancel out, and I would have just my x cubed times cosine of all of that stuff, and it checks out. All right. Well, I don't know about you, but I'm having a lot of fun doing these problems, so I think we should just keep doing some more examples. Next example, the indefinite integral of a square root of 2x plus 1 dx. So if this were just a square root of x, we could do this without doing any substitution. We would just rewrite it as a 1/2 power and do a power rule. But I have more than just an x under there, so we're going to use substitution. Let's let u equal all of the stuff underneath the square root. So then I can get my du is equal to 2 dx. And yes, I kind of skipped a step right here, but this is the standard way to do it. Remember, we were writing du dx equals 2, and then we multiplied the dx over. So I'm just jumping to that multiplication step. Now, if I were to do this the way I did the last problem, if we solve for dx, I get du over 2. So rewriting my integral, I now have a square root of u, and my dx is du over 2. And now, just like my last problem, pull the constant in the front. I have a square root of u, so that's a u to the 1/2, du, and now we're ready for our power rule. Remember, the power rule says add 1 to the exponent, divide by the new exponent. So I still have my 1/2 here, and I'm going to add 1 to my exponent, so I get a 3/2. And I'm going to divide by that 3/2. That's the same thing as multiplying by the reciprocal, 2/3. Then don't forget your plus c. We are going to simplify these fractions. 2/3 times 1/2 is 1/3. And then I have my u to the 3/2 power plus c. Plug your u in. U was 2x plus 1. And then we're finished. See, isn't this fun? We're taking problems that look pretty terrible, and it feels like we're cheating in a way. We're rewriting the problem and making it easier for us to work with. But it's not cheating because it's actually based in solid mathematics. It's something we can do to solve these problems. I think that's a lot of fun. Let's just keep on having fun, keep doing more. Antiderivative of x divided by square root of 1 minus 4x squared with respect to x. This one is another problem you're going to want to use substitution on. And in general, there's a lot of tricks for finding what your u should be. And honestly, that's probably the hardest part of substitution, is learning what to do for your u. This doesn't always work, but in general, if you have a square root with a bunch of stuff underneath it, have your u equal the whole bunch of stuff under the root. If you have a set of parentheses with a power on it, make u everything inside the parentheses. If you have like a trig function that has a bunch of stuff in it, u is the stuff inside of the trig function. Those are the types of things you want to look for when doing substitution. So we're going to let u equal all of the stuff underneath that square root. Then my du is equal to this derivative, so that's negative 8x multiplied by dx. And let's go ahead and solve for dx, just so that we can really see what's going on. So if I'm to rewrite this problem, we have an x on the top, I have my square root of u, and my dx is du divided by negative 8x. And look at that, the x's cancel out again, just like they're supposed to. So when I rewrite this problem, I now have 1 over a negative 8 square root of u du. And that still looks a little bit scary, but we know how to rewrite that square root with an exponent. A square root is a 1/2 power. It's in the denominator, so it's going to be a negative 1/2 power. So we get the integral of a negative 1/8 u to the negative 1/2 power du. And now we can use our power rule. We get to keep our negative 1/8. We're going to add 1 to the exponent and divide by that new exponent. Dividing by a 1/2 is the same thing as multiplying by 2. Add your c. Simplify by multiplying these numbers together. We get a negative 1/4. And then I have u to the 1/2 power. Well, my u was 1 minus 4x squared. And there's our answer. If you don't like writing your final answer with a 1/2 power, you can change it back to a square root and have it as a negative 1/4 square root of 1 minus 4x squared plus your c. That's perfectly fine, they're the same thing. All right, well I have, let's see, 1, 2, 3, I think 4 more examples to go, just to get some real good practice in. This next one's really not too bad. The indefinite integral of cosine of 5x dx. Now, I have a cosine that has more than just an x in it, so I'm going to use u equals the stuff inside of my cosine function. Taking the derivative, I get du is equal to 5 dx. And then if I solve this for dx, I get du over 5. So rewriting my problem, I have a cosine of u and a du over 5, which is the same thing as a 1/5 cosine of u du. Now we just have to find the antiderivative of cosine, but we know that that is sine. So I get 1/5 sine of u plus our constant. And all we have to do to finish it up is plug our u back in. So I get 1/5 sine of 5x plus our constant. All right. Just a few extra examples for us. Here I have 1 over 3 minus 5x squared dx. So you might guess, since I have a bunch of stuff inside of parentheses, that we should let u equal the stuff inside of the parentheses. Finding the derivative, I get du equals negative 5 dx, and we can solve that for my dx. Then, if I rewrite my problem, instead of a 3 minus 5x, I now have a u squared in the denominator, and my dx is du over negative 5. So I'm going to rewrite it with the negative 1/5 in the front. This u squared in the denominator is the same thing as u to the negative 2. And now I'm ready for my power rule. We get to add 1 to the exponent, divide by our new exponent. So I'm still going to have a negative 1/5, add 1 to the exponent, and then divide by that negative 1. Well, dividing by negative 1 is just going to change the sign to positive. Add our constant. So my final answer is a 1/5 times my u, which was 3 minus 5x to the negative 1 power, plus c, or we could move this 3 minus 5x to the denominator and write it that way. All right. Let's do just 2 more examples. They're going to be a little bit trickier. But just to show you how we can take some really complicated problems and make them not so bad. So we're going to have I didn't even make my integral big enough. The integral of 2x times the natural log of x squared plus 3 divided by x squared plus 3 dx. This looks terrible, doesn't it? That natural log is scary, but I also have fractions and multiplying going on. This is a real mess of a problem. Or is it? Think for a second, what's the most complicated thing here? Well, you might think the x squared plus 3 that's inside parentheses on that natural log. But do we really want a natural log in the problem still? Can you think of a function whose derivative is natural log? You're probably thinking 1 over x right now, but 1 over x is the derivative of natural log of x. It doesn't go the other way. So we really don't know what to do with that natural log, and if you don't know what to do with something in a substitution problem, hide it inside of your u. So I'm going to let u equal that entire natural log of x squared plus 3. And now let's do our derivative. We have to do a chain rule on this derivative. The derivative of natural log of x squared plus 3 is 1 over the stuff in the parentheses times the derivative of the stuff in the parentheses. So I get a 1 over x squared plus 3 times a 2x dx. If I were to solve this for my dx, I would have to multiply by x squared plus 3 and divide by 2x. All right, so now let's rewrite this problem. If I rewrite my integral, I had a 2x, my natural log is now going to be my u. I had an x squared plus 3 in the denominator, and now my dx is x squared plus 3 over 2x du. And that looks pretty terrible until you realize that the 2x's cancel out, and this x squared plus 3, they cancel out. And this horribly terrible looking problem that we had has now just become the integral of u du. That looks much simpler. Now, this is u to the first power, so using our power rule, we add 1 to that exponent, divide by the new exponent, so that's multiplying by 1/2, add your c, and all we have to do to finish it up is plug our u back in. And u was the natural log of x squared plus 3. And there is our answer. Now that problem was pretty complicated, but notice how even some complicated problems, once you use substitution on it, they end up being not so terrible. It's really actually pretty cool. All right, one last example to finish up this video, and be warned, this is probably my favorite example of all time for these types of problems. This was actually a problem that I had back when I was an undergrad. It was in our integration bee, which, yes, that's as nerdy as it sounds. It is like a spelling bee, but with integration instead of spelling. So this was from that, and I've remembered it all these years because I thought it was kind of cute. So our very last example, the integral of e times e to the x times e to the x dx. Isn't that beautiful? Lots of e's all over the place. All right, so what in this problem is the most terrifying part? And don't tell me everything, because that's not true. The worst part is this guy right here. I have an e to an e to the x power. That's a little scary. So let me hide its exponent inside of our u. Let u equal e to the x. Well, then what's du? Well, the derivative of e to the x is itself. So du is e to the x dx. And so dx is du over e to the x. Now, when I rewrite my problem, I have e times e to the u. And you might think, well, that's u as well, but I'm just going to leave that as e to the x, because then my dx is du over e to the x, and those cancel out. So now I have an integral of e times e to the u du. Don't let that e in the front scare you. E is just a number, so it's fine that we have a number sitting there. The antiderivative of this, we're still going to have our number e. Antiderivative of e to the u is itself, and plus your constant. And then we just have to plug our u back in. So I get e times e to the x plus c. And if you really, really wanted to, you could combine this together as e to the x plus 1 plus c by adding the exponents on our e's. But I always just left it right there. All right, so that was a pretty ridiculous problem, but I think it's kind of fun. Don't be too concerned about that last one. Be more worried about the ones earlier. Make sure you understand how those went. If you have any questions on substitution, feel free to ask them down below. If you're a current student, you may also ask in office hours or through email, and we'll get it all figured out. That's it for the videos for this week, and next week we're going to move on to a different type of integral called the definite integral, and we're going to do a bunch of stuff with those. So I hope you stay tuned, and I'll see you the next time.